barrier. So that is the overall procedure. For the silver example, this is the type of distribution that we get from finite number of trajectories. Here we have done about 3000 MD calculations. So the earlier FPT distribution I showed was in the limit of very large number of trajectories, but realistically one can easily perform calculations with a few thousands of MD trajectories. So, as you can see, the distribution is quite noisy, and so that means the estimates for the rate constants or the Arrhenius parameters will be noisy. But typically, the sampling error decreases quite rapidly with the number of transitions. So, as long as few hundreds of transitions have been witnessed for a particular path, the estimates should be fairly accurate. So for our silver hopping example, we analyze the FPT distribution and we can obtain the rate constant as well as the Arrhenius parameters. And here in this Arrhenius plot, we can see how the rates vary with the inverse temperature. So you can see that if we do not assume the any Arrhenius behavior, Arrhenius type behavior, then the temperatures vary in a straight line manner on this plot. And even with the Arrhenius approximation, you get the same behavior. So that means that indeed this particular path does display Arrhenius type behavior. And in this example, we achieve a speed up of about 500 times over the standard MD, which is pretty significant. Now, there is one more challenge which needs to be overcome while studying this silver example, which is that normally from a state, there can be several pathways. There can be some paths which are extremely fast because they are associated with low activation barriers. And then there could be other paths that are slow because there's a high barrier associated with them. And of these, maybe a few of these paths are of interest. So when we start doing the TPMD calculation, transitions are mostly observed along the fast paths. So very few transitions happen along the slow, high barrier paths. So this becomes a problem because you get very few transitions and the sampling is poor. So the estimates for the rate constants will be affected by the limited number of transitions that we're observing. So in the silver example, this is a different kind of state we are looking at. This is involving 3 silver adatoms or the trimer configuration. And there are many paths from this particular state as shown by the arrows. The detachment path, which is shown in the blue arrow, is typically of great interest, especially for problems in corrosion and leaching, dissolution. Usually the dissolution proceeds through detachment events, and this is a very slow, a rare event. In comparison, the dark line, the black line, is an extremely fast event. So in TPMD, mostly transitions will happen along these paths and not along the blue line, and that becomes very frustrating. So we need a solution for that. The solution is basically to block the fast process somehow so that there are no transitions along those paths. And we can block the other paths also, which are of less interest, so that transition mainly happen along the paths that are of interest. And so for our silver example, we can, for example, block all of these other paths, try to have transitions only along the blue arrow. So this step is achieved through the use of bias potentials, some blocking potential that can stop the move from happening. And there are 2 types of bias potentials that we use. First is a nonlinear spring that is applied to a particular atom. And this spring will really hold the atom close to its equilibrium position. And the choice of the nonlinear spring function is such that essentially it forms some sort of a bubble around the atom on which the spring has been applied. So within that bubble, the atom does not experience any force due to the spring, but as it approaches close to the walls of the bubble, it can feel the wall and it will stay within the bubble. The other type of potential we use is a wall potential. And so the wall potential, again, it's a soft potential. The atoms do not experience any force due to the wall when they are nearby. But when they come extremely close to the wall, then there will be some force. So the potentials are chosen in a way that we can still use reasonable empty time steps and while blocking the movement of these atoms. So by using three walls, for example, one can form a channel for the atom to move in the direction of the blue arrow. So with this use of the bias potential, it changes the FPT distribution, as you can see in this plot. The blue distribution is coming from without bias potential, and the green one is with the wall potentials. But even though the shape has changed, the predictions for the rate constants and the Arrhenius parameters is not affected. So you can see that you basically get the same answers with the use of the blocking potential. And in general, when we use these blocking potentials with different atom configurations, in our experience, the estimation of the rates becomes faster by an additional factor of 10 to 100 times using TPMD. So whatever speed up we were getting from TPMD, additionally on top of that, we get a 10 to 100 times speed up by blocking. So that is pretty useful.